welcome to my first vodcast on special relativity for the purposes of Unit 3 Physics in the VCAR study design. I should make a point clear at the beginning that what I'm actually going to cover in this first episode isn't actually special relativity as such, but it is foundational ideas to be able to build up our concept of what special relativity is. So it's an important episode just to begin this topic. So what this episode is will be relative motion of inertial reference frames, our goal being to relate the velocity of an object measured in one reference frame to its velocity measured in another reference frame. So there's sort of two things here that we need to get straight before we can get to the goal here. The first thing is to confirm that motion is relative, so we need to convince ourselves of that. And then we need to make sure that we understand or define what a reference frame is. So first of all, to convince ourselves that motion is a relative thing, just consider the everyday example of you and a friend being in a train. So let's say we've got these two people in a train. That train is moving along to our right with some velocity. So we have person A here and person B. So let's say we have Amanda and Brendan, just pulling names out of nowhere. And as you can imagine, when you're in this train, if these two people are standing in this train, they don't perceive each other to be moving relative to themselves. And the way that we can kind of define that or clarify that is to imagine that we have a sort of a big ruler or tape measure in our train. And so I'm just going to draw this in for the sake of being able to visualize that clearly. So say this is our ruler here. Amanda and Brendan, as the train moves along, will continue to measure their positions to be the same position that whole time. So their position is not changing as time passes, and that's what our definition of motion is, when position does change as time passes. But if we compare that to a person here, let's say person C, perhaps Carl, again just pulling a name out of nowhere, who's standing on the platform watching this train go by. Obviously this person thinks that the train and everything in it is moving. And again, we can clarify that by imagining that Carl also has a big tape measure along the length of the platform, and as time passes, of course, Carl will measure that the train, Amanda, Brendan, and everything in the train will be at different positions as time passes. So we can see then that depending on these two people's points of view, they're going to say that something's in motion or something's not in motion. And this is what we mean by the idea that motion is a relative thing. Hopefully that's clear then. So then we need to make sure that we understand what a reference frame is. So moving on to that idea, we've got a definition here. So a reference frame is any system where we could set up coordinates to measure position. So that's exactly what we had here. So if we just imagine a tape measure or something like that, that we can use to measure the position of things. It's worth at this point just specifying as well then what an inertial reference frame is. So this one here. Because that's what we're going to be dealing with when we talk about special relativity. An inertial reference frame is a reference frame which is not accelerating. Okay, so if we then move on to give a more specific example, all right, so let's consider now that train that is moving with Amanda in it. And let's say that the train is moving at a speed. So Amanda in the train and the train itself are going to be moving with a speed of 3 meters per second, say. 3 centimeters per second, I should say. So I'm just going to use some notation here. I'm going to say VA, comma, C. Now what I mean by that is velocity of A relative to C. Now C is, of course, our person down here, Carl again. Carl's got a cool little cap now. So the train relative to C, or Amanda relative to C, is moving to the right at 3 centimetres per second. Now, unfortunately, Brendan has turned into a ball, but it's handy because we can still use the letter B. Tough luck, Brendan. So this time, to make it a little bit trickier, and so we can create this idea of relating velocities between two different reference frames, the ball is moving. So say Amanda's rolled the ball and the ball's moving to the right in her reference frame. So I'm going to say velocity of ball relative to A at 2 centimetres per second. So the train as a whole is moving at 3 centimetres per second to the right, according to Carl. And then within the train, the ball is moving at 2 centimetres per second to the right, according to Amanda. So what we want to do then, and so say this is the situation at time equals 0 seconds. And just for simplicity, I've drawn this so that our reference frames, or the coordinates in our reference frames, happen to line up at this point in time. That's not necessary to get the result that we're going for, but it does make it a little bit simpler. So then let's say we want to know what happens, or what it looks like 1 second later. So if we consider this 1 second later, of course our train has moved to the right. And I think, given the simplicity of the numbers, you guys can do this without having to do the calculations. But just to be thorough, we can figure out how far to the right the train has moved. So we would say S, remember we use displacement, we use S for displacement. So displacement S is equal to change in time multiplied by velocity. And in particular, if we're wanting to know about how far the train has moved to the right relative to C, then that means we're talking about the displacement of A relative to C and the velocity of A relative to C. And we know that that is, as we go from this time to this time, that's a change in time of 1 second, and the velocity we know here is 3 centimetres per second. So we get a displacement of 3 centimetres to the right. Okay, and so that's what we've got drawn here. So we can see that our train has moved along 3 positions. It started here, now it's 1, 2, 3 centimetres to the right. Now the second thing we want to do is know how far the ball's moved. Well, we know that, so we can follow the same idea here and say the displacement of the ball relative to A is equal to the change in time multiplied by the velocity of the ball relative to A. Again, the time is 1 second. The velocity, though, of the ball relative to A is this one, 2 centimetres per second, which gives us a displacement of 2 centimetres to the right. So, and this is the displacement of the ball relative to A. So our ball started, as we drew it here, our ball started at a position of 2 in the train. If it's displaced 2 centimetres to the right in the train, then that means it's gone from here, 2, and then displaced 2 more to this position. So I'm going to draw the ball in this position. So it's still moving, but that's its position at this point. Now, we can then see what C has measured to happen here. So if we look at how C, or Carl, measures the ball at this point, Carl will see that the ball is at this point. So 1, 2, 3, 4, 5, 6, 7. So our ball is now at this point. And the ball started at this point, which is 2. So Carl measured the ball initially to be at a position of 2, then he measures it to be at a position of 7. So to figure out what the velocity of the ball is relative to Carl, then we just use displacement divided by time. So the displacement of the ball relative to Carl divided by the change in time. Again, that's just using our formula from up here. So that is, the displacement is going to be the final position, which is 7, minus the initial position, which is 2, divided by the change in time, which is 1. So we get 5 divided by 1, so 5 centimetres per second to the right. Now, all those numbers were pretty easy, but the result is really important to notice here, that the velocity that Carl measures of the ball, which is 5, is simply the vector addition of the velocity of the train relative to Carl, which was 3, plus the velocity of the ball in the train, which was 2. So we can summarize that by saying this. If A and C represent two different reference frames, so A is the reference frame of the train, C is the reference frame of Carl on the platform, and B is an object whose velocity we are measuring, so in this case the ball that's rolling along, then we can relate the velocity in the two reference frames by saying the velocity of B relative to C is equal to the velocity of A relative to C, so that is the velocity of the other reference frame relative to C, plus the velocity of the object within that other reference frame, so the velocity of B relative to A. Okay, if you have any questions or comments, please comment or do so below the video. In the next video, we're going to be looking at Einstein's two postulates.